What's up, everybody? How are you? I hope you're doing well. Today, let's talk about intermolecular forces. Now, we've spent a lot of time talking about atoms, molecules, elements, and even compounds. We talked about how in nature, atoms do not like to be by themselves, right? They combine together to make compounds, right? So we learned about how they combine, the rules, the formulas they make, the names of those formulas, the types of compounds. We talked about covalent and ionic compounds, and covalent and ionic bonds. Those are the bonds between the atoms inside the compounds, right? But guess what? If you take an atom and you add it to another atom and they combine to make compounds, guess what happens? Let's say you have this, right? So you have these two atoms, right? These are my two atoms, the red and the white, right? And then you have another two atoms that have combined, right? These are two compounds, right? If you put them together in water, guess what ends up happening? Chemistry, right? So they will either repel each other or attract each other depending on the chemistry, right? If you ever played with magnets, you know that magnets have poles, right? They have the north and south pole, and the another magnet will have the north and south pole. When they find themselves next to each other, they attract or repel each other, right? So the forces inside the magnets, there are forces inside the magnets, but then there are forces between two magnets, right? It's the same with atoms. There are forces inside compound. We call these intermolecular forces. Then there are forces between the compounds. We call them intramolecular forces, and then there are forces between the two. We call them intermolecular forces. So we're going to talk about some of these forces because guess what? These are the forces that govern a lot of chemistry. We talked about bonds. These are strong bonds, long lasting, that connect things. But these interactions that we're about to talk about are shorter lasting, they are weaker, but they happen way more often. We'll talk about why, okay? So we'll talk about the interaction between molecules, type of bonds that they make. But we'll also talk about how these molecules also interact together to make states of matter, right? And everybody here knows states of matter, right? Solids, liquids, gases. Why are things solids when others are gases? Guess what it is? It's the attraction between the two molecules. The attraction between the molecules is what makes them closer together. They pack together to make either a liquid or a solid. And if there are no attraction at all, they fly away. That's how we make gases, right? That is how we make gases. So I will start by talking about some of these intermolecular forces, and then after I will talk a little bit about solids and gases and some of the properties that we need to remember when it comes to solids and gases. So let's get started. All right, so this is an illustration of what I was trying to say. If you have H2O, this is an example, right? We already know how to draw this, we already know the geometry and everything. So if you have water, the bonds between water, and what type of bonds are these, by the way? Do you remember, are they ionic bonds or covalent bonds? Covalent bonds, right? Because water is oxygen and hydrogen, they are both nonmetals. So these covalent bonds are intramolecular bonds. But if you take two waters or a million waters in a cup of water, right, they are going to be attracting each other, right? and this attractive force is called intermolecular force, right? And this is actually what we see in water, right? This is what makes water what it is. All right, so again, inter and intramolecular forces, big difference, big distinction, right? So let's dive into some of these. So the intermolecular forces, right, are attractive forces between the molecules, right? And they hold atoms. So these are intermolecular forces, but intramolecular forces hold atoms together in a molecule. What's the difference? Let me show you the difference in energy, right? So if you want to break an OH bond, it's going to cost you 930 kilojoules. Very strong. But if you want to vaporize 1 mole of water, meaning breaking a bond between water, right? If you want to break this bond right here, is about 41 kilojoules, right? So this is like 20 times stronger, 20 times stronger, right? So this is the difference between inter and intramolecular forces, right? One is weak, one is very strong. One is long lasting versus the other one is short lasting. How about that? So let's start by what we call dipole forces. So I will be on page so that I'm listing them here. So I will be listing this intermolecular forces. So let's start with this dipole, right? Dipole. I think I'm going to give you like 4 different types, so I want to list them together here so that you have them. Dipole, very easy. This is the attraction between polar molecules, right? Polar molecules will attract each other. How? Think about it this way, right? This is the example that I gave earlier, right? So remember, polar molecules are molecules with an unequal distribution of charges. So let's say this is a polar molecule, right? It has a longer atom and then a shorter atom. This is what I mean by unequal distribution, right? So let's say you have HCl. This is your Cl, this is your H, right? If you bring another HCl, I have another one that has the same color, but if you bring another HCl here, right, guess what's going to happen? Because there is an equal distribution of charges, we already talked about how this is kind of negative, this is kind of positive, right? And if you have another one that has a positive and negative end, the negative end is going to attract with the positive end. 2 polar molecules will attract each other. Think of the magnets. Magnets have 2 poles, right? North and south. Same thing here. Polar molecules have 2 poles, right? Positive and negative. That's why we call it a dipole, right? Dipole attracts with another dipole, and we call it what? Dipole interaction, right? That is the first intermolecular force that we're going to talk about, right? As you can see, again, attraction between polar molecules, right? And this can happen in a solid, but this can and does happen in a liquid as well, right? It's called polar molecule. Now, another very interesting one is, what if you have a polar molecule and an ion? Right? Think about this, right? If you have an ion like sodium, right? And I want you to think about it and answer me, even though you are on video. But if you have sodium, right? If you have a sodium ion, let's say this is in a liquid, right? Do you think the sodium ion is going to be attracted to this part or to this part. The negative part, right? The negative part, why? Because positive attracts negative, right? So this is an attraction between ions and dipoles. And we call this what? We call this an ion dipole interaction. So let's write it down on our list. Ion dipole interaction. Ion dipole interaction is another weak force that we see all the time, right? Even water attracts or interacts with ions. This is why when you add salt in water, it dissolves. Why? Because the water ions surround Na plus and Cl. Remember, salt is NaCl, right? So ion dipole interaction, very important, very, very important. Now let me ask you this. What if our molecules are polar? Will there be any interaction between them? Big question. It's a big question that scientists wrestled with for a while, but we just talked about how things attract each other because they are polar, right? So you have like HCl and another HCl, right? They are both polarized. We know that this one is kind of partially positive, this one is partially negative. This one is partially negative, this one is partially positive. And because of that, the negative attracts the positive, right? That is a dipole-dipole interaction. But look at this. What if instead of having HCl, you have H2, for example, right? H2 is hydrogen with one electron. Now the hydrogen with one electron connect together. Is this molecule polar or non-polar? What do you think? It's non-polar, right? There's no unequal sharing of electrons. The sharing of electrons is completely equal at both hydrogens, right? There's no polarity. So if this is not polar, and you bring another hydrogen compound here, do you think these will attract each other? And for a long time, it used to be that it was no, because there were no interaction. But then scientists discovered that there is a force, very, very weak force that we call dispersion forces, right? So this one comes from something called temporary dipoles. Temporary dipoles. Temporary dipoles tend to confuse students watching. You want to understand, I want you to pay attention, right? So let's say you have a hydrogen, right? This is a hydrogen. Let's draw it like this, right? This is a hydrogen atom, a hydrogen molecule, another hydrogen molecule. It's non-polar at all. It's balanced, right? The charges are balanced. But when it comes into contact with something charged, when it comes into contact with something charged in a solution or in a container, that's something that's charged can give some charge to hydrogen. And when it gives some charge to hydrogen, guess what happens to hydrogen? Hydrogen becomes charged. It gets a tiny bit of charge temporarily. So that's what we call a temporary dipole, right? Temporary dipole. Temporary dipole. And when you have a temporary dipole, or we call it an induced dipole, temporary dipole or induced dipole, right? When we have that, then what ends up happening is that they have attraction between each other. So if you have different induced dipoles, they will attract each other, even though they were not going to be attracted in the first place, right? I hope you understand that. And all compounds have dispersion forces, right? All compounds can have dispersion forces, right? So let's see. Something that we call polarizability is how easy it is to induce this charge, right? And I want everybody to understand this. Why? Because when you have a lot of electrons, then it's easy to induce this molecule that would not have been polar in the first place. So let's write this down as well, right? This is called dispersion forces, right? Forces. These are dispersion forces. These forces, like I said, they are seen everywhere. Okay? So make sure that you understand where they come from. Make sure that you understand that they happen through temporary induced dipole. So that was dispersion forces. All right. So that's the third one. That's the third one that we talked about. And sometimes you hear people talk about van der Waals forces. That's another term for this, right? So let's look at an example. Right? This one is already answered, so it's hard. But I will give you a molecule like this, and then I will ask you, like, what type of intermolecular forces exist between this, and they might be more than one. So HBr, is it polar or non-polar? HBr is polar, right? So if it's polar, it will have dipole, right? But also, because we say that all atoms have dispersion forces, you also have dispersion forces. So you're going to have dipole and dispersion. What about CH4? CH4 is non-polar, right? CH4 is non-polar. We talked about this. So if CH4 is non-polar, it will only have dispersion forces, right? What about SO2? SO2, again, if you do its Lewis structure, you realize that it has a pair of electrons here, which gives it a bent geometry. Bent geometries are polar. So this SO2 is a polar molecule, and polar molecules will have dipole forces and then dispersion forces, right? Does that make sense? So we have these three, right? But I'm going to give you another one, even though it's related to the other ones. This one is called hydrogen. About 4 today. Hydrogen bonds, right? Hydrogen bonds are very special, very, very special. But even though they are very special, they, weirdly enough, are a type of dipole interactions, but they're a special type of dipole interaction, right? So hydrogen bonds are special dipole interaction, and they only happen when you have a high electronegative atom like nitrogen, oxygen, and fluorine. In fact, it's only these three, right? So hydrogen bonds happen when you have a hydrogen bound to only these three, right? So when this hydrogen binds to, not binds, because binds is kind of weird, but it attracts. When it attracts another molecule like this, we call this a hydrogen bond. And it seems to be much stronger than a normal dipole-dipole interaction, right? So as you can see here, for example, you have water, right? Water, as we've seen here, the hydrogens are kind of positive, the oxygen is negative, right? So the attraction between the negative of the oxygen here and the positive of the hydrogen here, this attraction seems to be very strong. It's a dipole-dipole attraction, right? If you remember, these are two dipoles. It's a dipole-dipole attraction. When the dipole-dipole attraction involves a hydrogen bound to nitrogen, oxygen, or fluorine, it seems to be very strong. We call that a hydrogen bond. All right? So hydrogen bonds are special. We love hydrogen bonds. And again, this is an example of this one is an acid and water, but again, as long as one of them is bound to oxygen, then it's going to be a hydrogen bond. I want you to understand that. And let's talk about this. Why is hydrogen bond considered special? And I'm not going to read all of this, but it is much stronger than your regular dipole-dipole. Much stronger, right? And also involves highly electronegative atoms. That's another reason why it's considered special, right? If you remember, what makes dipole-dipole interactions happen is this, right? My example of your dipole-dipole interaction, it comes from polar molecules that they have an unequal sharing of electrons. You remember, this unequal sharing comes from differences. What? In electronegativity, right? So if you have an element of a really high electronegativity, one with a really low electronegativity, they are the most polar, they have the highest polarity. And if they have the highest polarity, they will have the biggest attraction between the atoms, right? So high electronegative atoms are going to make these types of things, right? Another thing has a directional character, meaning that unlike other general dipole-dipole interaction, these hydrogen bonds have a specific direction going from one place to another. We call it a hydrogen bond donor to hydrogen bond acceptor, right? So these are kind of reasons why hydrogen bond is very special, right? So I can ask you this question, and this is a common question, like, hey, which of these can form hydrogen bonds with water? And I want you to pay attention, because look at this. The thing that forms the hydrogen bond with water is the thing that's also polar, right? So F2 will not form the hydrogen bonds with water because there's no polarity. CH4, even though it has hydrogens, they will not form hydrogen bonds with water because what? Because there's no polarity. Sodium will form dipole, it will form ion dipole interaction with water, right? But this one is the one that we just look at. It has a oxygen bound to hydrogen, right? This one has oxygen bound to hydrogen, and this will form hydrogen bonds with water because this hydrogen will be attracted to a water molecule, right? Does that make sense? I hope that makes sense, right? But this is a summary of these forces, right? Summary of these forces where you have, we already talked about ion dipole, hydrogen bonds, dipole-dipole, ion dispersion, right? We talked about dispersion, but we can also, by the way, this is actually interesting. You can have the you can have the ion and an induced dipole, or a dipole and an induced dipole together. So you can mix and match. But the major four that we talked about are these four. Make sure that you know them. Make sure that you know how they work. Right? Make sure that you know what they work, how they work, and what's going on. As you can see, an ion dipole is pretty strong, but hydrogen bonds are also really strong, stronger than your normal dipole-dipole interactions. All right. So make sure that you know this, and make sure that you understand all of these and how they work and how they differ, because I will definitely, it will be asked one way or another. But let's make one point clear before we go to the next, right? The next section, because I'm about to talk about solids and liquids and all that stuff. So we're not just talking about these intermolecular forces to talk about them. If things attract to each other a lot, right? Will they be easier to break or harder to break? They'll be harder to break, right? So if you have a liquid of things that attract to each other stronger, it will be harder to break. Then if you have a liquid that don't attract each other as much, it will be harder, will be easier to break, right? So that's why, for example, it takes a lot to boil water. It takes a lot to boil water, but it takes way less to boil gas, for example, right? If you boil gas, it's going to boil much quicker than water. Why? Because gas has low attraction. In fact, some gases are not even liquid at room temperature. That's why we call them gases, right? Because the attraction. So what we call boiling temperature is the temperature at which something boils. That goes with the strength of the molecules, right? Because if they are stronger together, the boiling temperature will be higher. That's why ionic compounds have a really high boiling temperature, because ion to ion, right? Then covalent compounds. Then we talked about ion dipole, and then dipole, hydrogen bonds. So it goes like this. So I will give you 2, 3, 4 things, and then I will ask you to rank them. And then we'll ask you like, hey, which one of these has stronger connection or interaction between them? And then I will ask you which one of these has a higher boiling point or a higher melting point. And the one that you will pick is the one that has the strongest bonds between them. Okay, so make sure that's why I make it clear that I want you to know which of these bonds is stronger, and then by looking at a compound to be able to tell me which bonds are present. Okay, that is the biggest take-home message. Okay, the biggest take-home message is that everything we see around us is governed by these. Because we make compounds, yes, but this cup of water, even though we learn how to draw the structure of water, this cup of water contains millions and millions of molecules of water. So we not only need to know how the structure of one water works, but the structure of the entire network of water and how they work together, right? But let's go to states of matter, right? So we'll start with liquids. So what are the properties of liquids? Liquids, I'm going to actually look at the properties of liquids in terms of a few words, a few definitions that I want you to actually remember. The first one is surface tension, right? This is one of the properties of liquid. And what is it? It is the tension on the surface, right? It is the amount of energy required to stretch or increase or break a liquid by 1 unit area, right? So on top, it's usually on top, but it's the amount of energy or force required, right? So if something has a high surface tension, it will be harder to break into, right? So this is one of the biggest properties of liquids, right? Another one is cohesion, right? Cohesion is the intermolecular attraction between the molecules, right? Cohesion is the intermolecular connection between the molecules that look the same, right? So between water and water, for example. But addition is the attraction between what? Between the molecules between one molecule and then other molecules that are different. So for example, we're talking about water. The cohesion of water is the interaction between water molecules, and the addition of water is the attraction between, for example, water molecule and the plastic container, or water molecule, oil molecules. Right? So cohesion versus addition. So we talked about surface tension, we talked about cohesion, we talked about addition, and one way to think of cohesion is water is attracted to water. Addition is water is attracted to other substance, right? So those are the properties. Another property that I like is viscosity. Viscosity is defined as a resistance to flow, a measure of a fluid's resistance to flow. And I like that. I like that definition, but as if I call it like stickiness. Water is not sticky, but oil is a bit sticky. You know, when you pour it, it doesn't pour fast. So it's the resistance to flow. Between water and oil, which one do you think has the highest cohesion? Oil, right? Has to be oil. What else do you think has more viscosity than oil? You think of something? I don't know, something like lava, you know, something crazy like that. But think of viscosity like that, resistance to flow, right? Now I have a whole lecture about water itself. Water is a very unique substance, right? When it comes to liquids, water is basically one of the most special liquids. And one of the reasons why water is the most special liquids is because, like I said before, it's the medium of life, right? There's a reason why whenever we go to another planet, we look for water first, because without water, there is no life. We are 75% made of water, right? Water is a solvent, and one of the reasons why is because water is polar. It has a high polarity, so it dissolves and binds a lot of things. Almost everything can dissolve in water. We use it in the lab a lot because, again, almost everything can dissolve in water. And not only that, water melts and boils at the perfect temperature when it comes to human life, right? And another reason, another big reason is that its density is really good and doesn't change that much based on temperature. And guess what? The way water forms ice is very special. This is actually important. The way water forms ice makes it so that ice is less dense than water, right? So whenever water forms ice, it makes these kind of crystal-like structure, right? This crystal-like structure like this to leave room for water, to leave room so that ice is bigger than water. Leave room so that ice is bigger than water. All right, and this is, you know, I really like that. I really like that characteristic because it has made life on Earth possible, right? Because if you know anything about the history of the Earth, you know that a lot of animals developed under ice. If there was no ice floating above water, life would not have developed on Earth. I could talk a whole hour about just that, but we'll talk more about that. We'll talk more about that when we get there. But liquids, very important. Liquids are the medium of life. Liquids are characterized by, as we talked about, surface tension, cohesion, adhesion, viscosity. And also another thing to remember, by the way, is that liquids, right? So we can I don't think I have it here because you've done this before, so it kind of goes without saying. But difference between gases, liquids, solids is the attraction between the molecules. The solids are like right next to each other. Liquids are spaced out but not too far apart. Then gases are all the way like this. So much gap. That's it. So if you zoom in into these, that will be the difference. But now that you've learned about intermolecular forces, we know why exactly have liquids, solids, and gases. It's because of the attraction. The attraction comes from the chemistry, from the polarity, from the ions, and all that stuff. So let's talk a little bit about solids, which are just right next to each other. So the solids are usually two types, right? Let's talk about two types of solids, right? Two types of solid. It can be a crystalline solid. Crystalline solid is exactly what it sounds like. It has little crystals. Right, yes. Okay, so it has little crystals. Solids has little crystals. An amorphous solid does not possess a well-defined structure, right? So you will see something that's randomly distributed. That will be your, if it's like a randomly distributed solid like a rock, that would be amorphous. But then every now and then you find like something with like some nicely neatly constructed crystals. These are crystalline solids, right? And you can see an example. Even your book goes through like the different types of shapes. I don't really care about the shapes, to be honest with you, but some of them are pretty neat. And there are, if you want to like count them, there are types of cubic unit cells, right? So you can have a simple cubic like this. You can have a cubic called a body centered, where you pack more, and then you have even a face centered cubic where you pack even more, right? I don't think that we need to go further than that, but these kind of give us a model for the arrangement of spheres in a cell. And again, I will not spend too much time on this. I don't think that it's that important, but it is important because that's how a lot of solids are packed. But I don't think that we're gonna have to calculate this. I don't think I'm going to have you calculate this. Yeah, I don't think so. I don't think. Just know about this, but we're not going to spend too much time on this. But let's say if I give you like gold, and then I tell you like, hey, it crystallizes in a cubic closed packed structure, right? You're going to go and be like, okay, what's the cubic closed packed structure? All of them, I'm going to find which one is a closed packed structure. Where is a closed packed? We're going to find one of them. I think it's the face-centered cubic one. And then from there, you can figure out how many atoms per unit cell. Then from there, you can find the atomic radius, right? If you have the density, you can find the atomic radius. If you have the length of the cell, you can calculate the density, because you can find the volume. That's all I'm gonna say about that. Don't worry about that. But that's how you find the volume of the crystal structure, right? Now, how do they find these types of these crystals? You do what we call X-ray crystallography, right? Where you put a crystal in here. So it's kind of like how you do X-ray, by the way. If somebody has ever done an X-ray, there was my last class that I taught. I asked everybody like, hey, has anybody done an X-ray? And almost everybody raised their hand. I was like, what happened here? Because usually most people don't do X-rays, but you can have an X-ray of a crystal. where you put a crystal here, you shine an X-ray here, and then you see the pattern, and then from the pattern that you get, you can figure out what type of crystal it is, right? It's called X-ray crystallography. We even get structures of proteins this way, but there are different types of crystals, right? This I want us to know, right? We want to be able to know that we have ion crystals, and ion crystals are crystals of ions, exactly what it sounds like, right? These are crystals made of ions. So sodium, for example, sodium chloride is an ion crystal. So ion crystals will be crystals of salts, right? Salts. So as you can see, these are ionic compounds. We call them salts, right? Like NaCl, CaCl, ZnCl. These are ion crystals, right? Ion crystals. And then you have covalent crystals. What do you think those are? They are made of covalent compounds, right? They are made of covalent compounds. They are made of non-metals, right? Non-metals. So for example, this is carbon atoms. If you know about this, you know that when carbon atoms get together, what do they form? They form gold. That pass you like, not gold. Why did I say gold? They can form diamonds. Diamonds are made of carbon atoms. But also they can form graphite, they can form charcoal, depending on what type of crystal they are. These are called covalent crystals. We have ionic crystals that are made of ionic compounds, covalent crystals that are creating atoms of non-metal compounds, and then you have molecular crystals. Molecular crystals are made of molecules. So covalent crystals are made just of atoms, non-metal atoms bound together, but molecular crystals are made of molecules. This molecule bound to each other, and they are held together by intermolecular force. Then you have metallic crystals. What do you think those are? Made of crystal. Made of, not made of crystals, of metals, right? A lot of metals are crystals, by the way. A lot of metals are just bound together. A lot of metals are crystals. So types of crystals, like I said, have ionic crystals, covalent crystals, molecular crystals, and metallic crystals. Make sure that you know these. Make sure that you know these. You know what they are, what they are made of, and things like that, right? Make sure that you know that. Very, very important. And again, you can have an amorphous solid that does not have a well-defined arrangement. A glass is an example, right? Glass is an example where it's kind of random arrangement, right? So again, remember, we have two types, right? When it comes to solids, we have two types of solids. We have amorphous solids and then crystalline solids. And when it comes to crystalline solids, we have 4 different types of crystalline solids, right? Metallic, ionic, molecular, and what's the last one? Covalent, right? So those are the 4 different types of crystals, right? So make sure that you remember this, make sure that you know how to define this, make sure that you know the difference, and make sure that if I give you an example, you'll be able to tell. Now let's go back to different phases and talk about something called phase changes. Seen this before, right? Going from one phase to another, you've seen this before, and be sure to be able to define this, right? Whenever you go from solid to gas, it's sublimation, and you know, you can like this, but there is one that I like that is kind of a circle. They are all the same, right? From solid to liquid, melting. From liquid to solid, freezing, right? These we know. But from liquid to gas is vaporization. From gas to liquid is condensation, right? The ones that are not popular are sublimation and deposition. You might actually have not seen sublimation. You've seen deposition, for sure. When you see, like for example, you see the deposition of, like when you wake up in the morning and you see the leaves have water, sometimes it's from water going directly from gas solid. It's tough actually. I don't know if you've seen this before, but sublimation is also, we've seen this with iodine. Iodine does this. But again, make sure that you know these 1, 2, 3, 4, 5, 6 solid changes, and as you can see, they go up with increasing temperature. So make sure that you know that, right? Now, when it comes to liquids and these phase changes, another thing that I want you to know is vapor pressure. So look at this. Again, you have condensation and evaporation, right? Going from liquid to gas, you have condensation and evaporation, right? So when you have a liquid, say water, and over time, it's increasing, right? So you have an increasing level of condensation, right? And then you have a level of evaporation. When they get to where they are at the same time, then we have reached what we call equilibrium vapor pressure, right? This is when the rate of condensation is equal to the rate of evaporation, right? So this is an important, very important term, chemistry, that we like to measure, we like to keep. This is another term that I want you to know: equilibrium vapor pressure and vapor pressure in general. And we have different machines that we can use to measure it as well, right? But that is what it is. So we care about this because you can use it to measure what we call the molar heat of vaporization, right? What is the molar heat of vaporization, right? The molar heat of vaporization here is the energy required to vaporize 1 mole of a liquid at a boiling point, right? So how do we calculate it? We use the pressure, right? We use the pressure, then this is the one we're looking for. Then you have R, you have T, and then you have this constant, right? So this is equation called Clausius-Clapeyron equation. Use this to measure this, and you can kind of convert it because this one is a bit weird. It's a bit weird, so we don't use this. So if you want, we actually use this equation, right? Where you have 2 temperatures. So you have 2 temperatures. You want to measure the heat of vaporization. So you have pressure 1, pressure 2. You have temperature 1, temperature 2. You have R. You can use it to find delta H vap very, very easy and very quickly. Very easy, very quickly. We do this all the time, right? So as you can see, we have different types of boiling point and different type of energy of vaporization, right? Molar heat of vaporization, right? Again, different compounds, different boiling points. And if you remember, we talked about how these boiling points, the differences in these boiling points usually comes from where? From their intermolecular attraction. All right. So another thing too, and this actually some people don't get this point. Don't, but the vapor pressure changes the boiling point. I repeat, the vapor pressure, the pressure in general, changes the boiling point. Right? I've seen this guy actually do the experiment where if you boil water here, like wherever you are right now, if you boil water, it will be around 700 degrees. If you go on top of Mount Everest and you boil water, it will not be at 100 degrees Celsius. I promise you that it will be lower. So the more you change the pressure, the more the boiling point changes. So that's why actually whenever we're talking about boiling point, this is the temperature at which the equilibrium vapor pressure of a liquid is equal to the external pressure, because this is what pushes the liquid to start boiling, right? It's just that the normal boiling point, we measure it at 1 atmosphere, which is our pressure around us. That's why whenever you go up the mountain, the pressure changes, and when it changes, the boiling point changes. Very exciting. Everybody needs to know. All right, so yeah, I can tell you more about this. The critical temperature is the temperature above which the gas cannot be made to liquefy, right? No matter how great the applied pressure. So if you reach the critical temperature, then the gas will not become liquid, even if you add as much pressure as you can. Right? Same with the critical pressure is the minimum pressure that must be applied to bring about the liquefaction at a critical temperature. Right? And I will show you in a minute what we use for that. Right? So what we use for that is something that we call phase changes. Right? So we have different phases. Right? We already know this: gas, liquid, solids, right? So for example, water has 2 phases, right? And these phases, when we talk about phases, we talk about like a homogeneous part of the system, kind of separate. It's separated from everything else. It's well defined. It's not mixed with other things, right? For example, a solid phase, that is ice; liquid phase, that is water, right? But we also have a gas phase as well. So to illustrate this, we do what we call a phase diagram. Right? This is a diagram. I want everybody to be familiar with this, because this is one of the most common things in chemistry, especially Gen Chem 2. Phase diagram. You can see it well. All right, so this diagram, if you look closely, has temperature here and has pressure here, right? It's talking about how it changes, how the point at which water is solid or liquid changes based on what? Based on temperature and pressure, right? Because guess what? Look, when you have one atmosphere, which is our atmosphere, you're at 0 degrees Celsius, right? Water is a solid, right? Water becomes a solid. But guess what? Water can become a solid at a lower temperature if it has a lower pressure. So it's going to become a solid in all these regions, right? So if I ask you like, hey, what is the state of water at negative 10 degrees and 0.5 atmospheres, it will still be solid, right? And guess what? Same pressure but higher temperature. What happens to that solid? It melts, and now you have the liquid. And this what happens at a higher temperature? It becomes vapor, it becomes gas. But as you can see, you can have gas even at 0 degrees Celsius if you have very low pressure. If you have very low pressure, water will become gas even at low degrees Celsius. So this is called a phase diagram, right? It looks like this, and here are some of the things that you can see, because guess what? I will give you a phase diagram, and I will ask you some of these points. It won't be for water, it will be for something else, right? But look at this. The point at which, right, a point at which you have a gas, solid, and liquid. It's called triple point. Triple point, right? It's pretty cool, right? At this point, meaning at this pressure and temperature, you can have mixture of gas, liquid. I love this. But then you go up here, you have the normal melting point, right? And then at this, you go here, you have the normal boiling point. So melting point here, normal melting point, because you are at 1 atmosphere, right? 1 atmosphere. So 1 atmosphere, when it hits here to this line, the boiling point. Why boiling point? Because we're going from solid to liquid, right? That's boiling. And then you keep going at 100. That's when you hit the boiling point, right? The boiling point, which is going from liquid to gas, right? So again, that is the kind of things to look for when we're talking about a phase diagram. You also have critical points here, and then up here you have what we call the supercritical fluid. Very interesting stuff. I don't think we have time to talk about that, but just know about these, right? So you have the triple point, for freezing and melting here, vaporization and condensation here, you have sublimation and deposition here, right? And then at 0 here you have the normal boiling point, 0, 0 and 1 atmosphere. And then here you have 1 atmosphere, and 100 is the normal. So this is the normal melting point because we're going from solid to liquid. This is the normal boiling point from liquid to gas, right? So let's see, 1, 2, 3, 4, 5, 6, 7, 8 triple points. So I can ask you like 8 or 10 different things. So I'm telling you this right now, I will probably give you an empty one, and then I'll ask you to add like, hey, add 10 different things here. Because I can also ask you like, hey, add, tell me which one is solid, which one is liquid, which one is gas. So I can ask you to label 10 different things here. But not only can I ask you that, I can give you one like this, and then I can ask you like, hey, what is the melting point of this liquid that I give you, this substance, or like at this temperature, is it going to be liquid, gas, or vapor? So make sure that you know that as well. Make sure that you know that. Make sure that you know how to read all these phase diagrams. A crucial part when it comes to chemistry. Okay, all right, what else did I want to talk about? I think that this is enough. Actually, I think this is enough. Make sure that, again, take good notes, write down what you don't understand. Let me know if you want me to clarify this further. You can always, again, rewind these videos. That's why I make them. And if you need me to cover something else, just let me know, guys. But other than that, I will see you in the next one. Bye.